Well, I think we're done here, and I said this will take like 10 to 15 minutes. I'm really sorry. And now I think I'm done, and I want to welcome up on stage Martin Thompson, the creator of Disruptor. I have a keynote about mechanical symphony. Welcome.
Thank you very much. And thank you for inviting me to this wonderful conference. I had no idea this even existed a year ago. And I met this guy in Crete where it was a bit warmer than here the last time. So I'm going to start off with a very simple question. Who likes slow cars that use up lots of fuel? Yeah. Maybe that explains all the software in the world. Because we seem to make software that is very slow and use up lots of energy. So what this talk is going to be about is this guy, a guy called Jackie Stewart. He coined the term mechanical sympathy, which I'm going to talk a bit about. And I think there's wonderful things have happened in the automotive industry that we can learn from in the software industry. I'm a big petrol head, so confession up front, full disclaimer, I'm going to talk a lot about cars. So if you don't like cars, I apologize a lot in advance. But there is some really good stuff from this that works for software, and we can learn quite a bit from it. So this guy, through the 1960s and 1970s, won 3 world titles, and he only raced 99 times. There was a reason he stopped, and I'll get on to that in time. But probably one of the best drivers of all time, could have achieved a lot more, but he done a lot for the motor racing industry, and he done a lot for how to run an industry like that we can learn a lot from. He was known as the Flying Scot, from Scotland. And one of the things that he used to do that was very formidable was in the wet, he was faster than anyone else. This picture is from the Nürburgring circuit in 1968. He completed the race, winning the Grand Prix that year. He was more than 5 minutes faster than the second place driver. He was more than 10 minutes faster than most of the field, finishing the race. Now, he wasn't racing against a bunch of idiots. The rest of that race included people like Graham Hill, Jack Brabham, Bruce McLaren. These are names you may know if you follow motor racing history. Many of those world champions in their own right. He just stood out from the rest, particularly when it was wet. And a lot of that came down to how well he drove and how good his understanding was of the car. And he turned that mechanical sympathy. His description was it was man and machine working together in harmony. I think there's a lot to be learned from this in software. He also postulated at the time that we had reached a point whereby most of the drivers did not understand their cars, and this was becoming a problem in motor racing. Up until that point, a lot of the drivers built their own cars, worked in teams, had great understanding of these vehicles. Around this period, it was getting to the point where drivers were driving cars that they didn't understand because they weren't involved in the building process. Any of this sound familiar in software? That we're now using a platform that we have very little understanding of? Where if you played with computers in the 1980s, you probably built the same computer yourself. I did. I soldered my first ZX81 together. And I wrote assembler on it. It was really good fun, and I learned a lot about how they worked. I think very few people today actually build the hardware that they write their first programs on. So what does a hardware guy look like in motor racing? Well, at this time, Colin Chapman was the best designer of cars. Today, we may say it's Adrian Newey. But Colin Chapman was the hardware guy of that time. He was a structural engineer. He also specialized in aerodynamics, and he'd done a number of things for cars that is now standard, like the monocoque suspension in a car was one of his inventions, having aerodynamics underneath the car, reducing weight, knowing that reducing weight is much more important than adding power. And I think that's an interesting thing to take through in software. So often we add when we really should be taking away. Because the ideal spacecraft, the ideal race car, the ideal aeroplane is the one that you can not remove anything more from, not what you can add to it. I think software can be benefiting from this sort of thinking. So can our sort of tame racing driver understand what was going on inside those cars? Let's ask the guy himself, Jackie Stewart. He thought so. He thought definitely drivers can understand this, and by understanding it can get a lot more out of it. I'm going to leave this quote for the first section, and I think this is great. This is from a good friend of mine, Dave Farley, who wrote Continuous Delivery, where he made this comment once in a forum that he cannot think of no field of human endeavor that allows the levels of inefficiency that we accept as normal in software. And I think it is very true. I can't think of anything else that allows multiple orders of magnitude of inefficiency. It's not like we need to chase those last few points all the time. We're just wasteful beyond belief. So, what are we going to cover for mechanical sympathy? We're going to cover 5 things. I want to talk about how we model, because this is very relevant to understanding what's going on underneath. Also, how we deal with safety. Safety in motor racing was one of the big fundamental changes that Jackie Stewart brought in. There's also a lot from that we can learn from how our software operates and the hardware platforms operate. By understanding the safety, we can understand that a lot better. Talk about testing and how relevant that is. Also, the data that we need to back up our testing and understanding when we dig in further. And finally, I'm going to talk about putting this all a little bit together and putting it into action. So let's start off with, let's distill a model. Now, if you're from a domain-driven design background, you may say what modeling is something like this. A model is a representation of the domain in a given context. That's a fairly nice way of putting it. The scientific view of the world may say, well, it's a simplified, abstract view of a complex reality. I like to think of it as the important shit you need to know about how stuff works. And capturing that important stuff, because that's what matters. So how do I create a model when I go about doing something? So I want to deal with something. So I want to distill what represents that model. Let's take an example. How would I make a really fast car? Teenagers these days think that will make a really fast car. They will stick lots of plastic on it. They'll put shiny wheels. They may put a very large stereo inside it. And it'll drive down the road going boom, 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 boom. It's not going to be very fast. So much software looks like this. We add stuff to it. It's wrapped up in fashion and craft and follows this. Really fast looks more like this. That little car only weighs 550 kilos. It has 500 horsepower, made by welding 2 motorcycle engines together. It will do 0 to 100 kilometers in just over 2 seconds. It strips everything out. It only puts in what is important. That's the essence of what makes a very fast car. And that will go around a track much faster than one of those. So how do we do this? How do we come up with the models of what's important? We break it down to just 3 very simple steps. One is we want to draw on our own experience and the experience of our teams. That's how we go about building these things and making them interesting. That's typically what we're doing, but quite often we don't know everything. It's not quite often, it's virtually all of the time we don't know everything. So we need to do research. And we should do a lot more research and actively plan it into what we're doing. But we also need to experiment, because even when we read research, we need to test it and experiment that is giving us what we want. And from there, we can build and refine models, and I'll go into more detail. So let's distill some models for some domains and get the fundamental understanding of what's important. So I've spent a fair few days on racetracks. I like cars. I've gone and had lessons for driving race cars, and I've been taught how to take a corner very fast in a car. I seriously recommend anyone does this, not just for the fun of it, but it will make you a much better driver on the road because you will understand how your car works. So, simple example. I want to turn around this corner. So if I'm going to take the corner, one of the things I want to do is make the radius of the turn as large as possible. So I'll use the full width of the road. So I'll start off on the outside, come to the inside, go out again. That's kind of step 1, nice and simple. What's more interesting is how I apply brakes and how I apply the throttle for acceleration. So one of the things I do not do is once I get into a corner, I do not start braking. Because if I start braking, bad things are going to happen. You get under a panic when we're driving around a country road and it's a little bit sharper than we expect. We panic and we brake. And that's usually when someone goes through the hedge and has a crash. There's good physics for that and why that actually happens. What you're supposed to do is go up as fast as you can, then brake really, really hard in a straight line. So just before you reach the turning point, you must have stopped braking. At this stage, your foot's off the brake and you're steering around the corner. As you steer around the corner, when you pass the apex, you can start applying acceleration to get out of that corner. Now, why does this all actually matter? It's because of the physics of what happens to a car going through. So as I'm going around the corner, look, the car dips over. It applies a lot of pressure to the wheel, and it'll lift this wheel. Now, if I'm going around a corner and I was to brake whenever the cars are ready in this configuration, what's going to happen is this wheel is just going to lose traction and slide. So you don't want to be braking once you're going around a corner. What you actually want to do, and this is counterintuitive, is accelerate. Because if you accelerate, the force goes backwards, and this wheel will come down onto the ground and give you more traction. So this is a kind of scary thing to ever do. So if you ever find yourself out on a road and the bend is sharper than you expect and you go, panic, don't brake. Hit the throttle and you'll probably make it round the corner. You hit the brake, you'll probably go through the hedge. So that's just understanding the physics of what's going on. That's how cars work. Let's look at something that we all kind of know and love. We want to write to disk. So let's understand what's going on whenever I write to disk. So I've got my spinning Rust down here, and it lays out all of my data in sectors on that. And somewhere in between here and here, stuff happens inside our operating system. What actually matters? Well, most people believe magic ponies come in and stuff happens. Is that the important stuff that we need to know? Well, not really. What is actually happening underneath it is a number of things. All of these little sectors on the disk map into pages that are held inside our operating systems, and we read and write to these pages, and a set of threads writes it down as efficiently as possible to there. So it starts becoming really important knowing, what are the sizes of these? What are the sizes of these pages? And am I starting to write at the beginning and end of these? And that's how you get a lot of performance and a lot less surprises out of things and how they work out. And it doesn't actually take too much to learn this. So you can have a little bit of time, learn these sort of things, and get a lot more out of your operating systems, just as soon as you can get a lot more out of your car by understanding it. You don't need to be able to write kernel modules. It's just about understanding the basics. And we don't need to live in this world, which most people do. But that's fine. How do we find these things out? Well, we read. We do our research and we read books like this, and this will tell us what's going on. And then we know how to get the best out of something like our operating system and how it writes to disk. But the thing is, we should just do what is required and nothing more. Like Colin Chapman, he used to design cars to win races. One of the things that he realized was so important to winning the races is that a car should be as light as possible, have the minimum mass as possible. So one of the ways he did to test that was he drilled holes in them. That saves weight. He took the chassis and he drilled lots and lots of holes. And the ideal car was the one that completed the race and fell apart just afterwards because it had just done enough. So when I'm saying go take the time and learn this stuff, I don't mean devote years and years of your life to it. Just do enough to get the job done, but know enough to do it. So we have a model. If we want to actually understand more about the model, quite often understanding the safety features is a very useful thing as well. So here's a really good example of why safety features are very important for motor racing. 1966, Spa in Belgium. Jackie Stewart was racing in that race. And at one point, this ended up happening to him. He went off the track at 165 miles an hour, went through the trees, through a telegraph pole, and landed in the outbuilding of a farm. that was nearby. He was trapped for 25 minutes inside this car with fuel spilling into the cockpit. There was no safety crews at the track in 1966. There was no medical team at the track. There was not even crash barriers. That's why he went off the track at this rate. He said for 25 minutes with petrol pouring onto him, panicking, thinking he's going to die, he could not get out because the steering wheel had jammed against his knees and he couldn't get out of it. The reason he lived that day is his teammate stopped his own car he was racing, which was Graham Hill. Graham Hill got out of the car, found a truck with a toolbox, and screwed the steering wheel out of the car and pulled him out. He also stripped him naked because he was covered in fuel, because people were standing around smoking, watching what was going on. Also, just for full embarrassment, if we ever think our job's embarrassing, as he stripped naked lying on the grass, Graham Hill goes to get help, and the people who looked after him were nuns. Poor guy. You had to get pretty thick-skinned after that. Ever since that event, he used to race with a spanner taped to the steering wheel in case he ever needed to get out again. Unfortunately, he also lost many friends. Probably the greatest driver of all time, Jim Clark, another fellow Scot, died in that same era. And the reason he only raced 99 times is he planned to race 100 times, but he had already won the season in 1973. And during testing that morning, his teammate, Francois Cheever, died as well. And he decided not to have his 100th race with Jackie Stewart in this time. These people were crazy. Here's a fact of that time period. Back then, if you were racing, you would have a 2 out of 3 chance of killing yourself within 5 years. It was worse than being a fighter pilot. These people were nuts. Brave, but nuts. Jackie Stewart wanted to change that and make it much better. So he brought in a lot of thinking about safety features, and he retired after 99 races to dedicate the rest of his life to improving safety in motor racing from that point forward. And he did a lot for it. Not just for what he did for the sport. We benefit so much now because of so much of what happened back then. Things like crumple zones in our cars, disc brakes, seat belts, the standard of modern crash helmets, that all has come about from a lot of the work that Jackie Stewart and a few others have done. So all of these things did not exist in 1973 when you were racing. That is terrifying. He got a lot of that sorted out. But what he found through a lot of that is bringing in change was incredibly difficult, and he had to be very brave. There was 2 good reasons why people didn't want things to change. One was the fact that all of these people who are dying made wonderful television. The television companies didn't want all the safety features coming in, and they were willing to have the sponsorship and all happen because this was exciting. It was gladiatorial. But also the racetracks didn't want the change to happen because that would involve lots and lots of cost. Jackie Stewart was actually accused of not being man enough and not having bravery for racing. That race he had in 66 where he was more than 5 minutes faster than the second person and more than 10 minutes faster than everybody else in the field. The rest of the drivers got together and said, that is complete rubbish. He's one of the bravest drivers out there. He's just trying to fix this for us and try to make it better. And sometimes whenever we're changing stuff, we have to realize that change is hard. It's always hard. And there will be people who say no and people who don't want it to happen because it's a very natural thing and you have to be brave to fight it. I think this comes down to some interesting things about our jobs when we look at how we change things. And it is like, is it actually a job or is it a vocation, what we do? Because I think the level of complexity and the level of interest that you need to have to get really good at what we do, it's not just a 9-to-5 job. Technology changes so much. There's so much to learn. It's not like we just learn our craft and that's it. You have to be passionate. You have to be dedicated to this. And we have to end up changing many things sometimes to get better at what we do. But by actually spending some time on the safety features, we can learn a lot. We learn a lot about our underlying platforms, and I like to use the safety features as a means of helping me understand and improve my models. So if you look at some of the underlying safety features we have in our modern platforms, I'm just giving some random things up here, almost like bounds checking that we have in, say, managed runtimes for languages like Java and C#. Understanding how that's applied, how it's actually optimized away, when it's applied, when it's not applied, is fascinating for understanding how a runtime works. Same with things like garbage collection. If you get into things like networking, how does congestion control work? How does flow control work? How does things like replication work? These things are fascinating and really interesting to study and learn about. And if you take the time to learn some of these things, I think you get two major benefits. First up, your software becomes so much more robust because it doesn't suffer surprises from this underlying platform. It actually starts to work with it. And it also gets so much more performant because it makes the right use out of what goes on underneath. So taking the time to understand a lot of this is really, really valuable. But again, it's just take the time to understand enough about it. You don't need to become the complete expert. It's understanding enough to become useful with these things. And they'll reinforce your models and make your models stronger. So let's move on now to the importance of testing. What happens if you don't do enough testing? Well, this was Mark Webber at Le Mans in 1999. Mercedes did not do enough aerodynamic testing of this car. That's not a crash. He's driving at over 200 miles an hour down the straight, and the car just went into the air because the aerodynamics was wrong. It's got to be kind of scary. What actually happened is that flipped over and went that way sideways across into the trees. I should actually show the video of this. It's far more dramatic than that single picture. Mark Webber lived from that because safety features got so much better in our cars. 10 years later, he was also doing 200 miles an hour. Same guy. Unfortunate Aussie. And that happened to him where he touched the car of Heikki Kovalainen, the Finnish driver. And what did it look like from inside his car at that point in time? Where's the road? The same thing happened in both of those crashes. He broke the brake pedal. As he went airborne in both cases, he hit the brakes so hard he broke the brake pedal. It isn't going to help him, but he has no wheels on the road. Again, that was not enough testing of what happens in open wheel racing whenever you touch the wheel of the car in front. This year we're getting changes to the front of Formula One cars to try and prevent the likes of this happening. There's a lot more work on aerodynamics has been done so the likes of what happened at Le Mans and stuff doesn't happen again. So Formula One learns from these things. All motor racing does, and we try to get better. Well, what about software? This is that's all nice and spectacular. Do we do silly things in software? Mars Climate Orbiter? $175 million because people didn't convert imperial and metric correctly? Oops. How about this one? Ariane 5. Overflow. For 37 seconds after takeoff, we enjoyed each second of that flight was worth about $10 million. Before that went pop as well. Again, a software bug. Or this one. $460 million night capital. So our software can be quite special as well. What's getting quite scary is as the world goes forward, the software that we are writing is having huge impact. We have so much more control over what's happening in our world through software that when we start seeing large-scale bugs, the repercussions are terrifying. We could take out complete financial markets. We can destroy satellites. We can do all sorts of crazy stuff, and more stuff's getting controlled this way. As we get into the Internet of Things, what else is going to be controlled? So our software better be tested a bit better, or it's going to get very expensive. I like to think of testing as my way of building confidence in a model. So I've got a model, I want to build confidence, and testing is the way to do it. And it's a bit like applying science. If anybody hasn't read any of the work of Richard Feynman, I seriously recommend it. It's so entertaining as well as being so informative. But he talks about the pleasure of finding stuff out. Testing can be wonderful fun, especially testing for performance and resilience and lots of other really cool stuff like that, because you find out so much about how things actually work. And this gives us the experimental evidence we need for our models. Now, quite often testing is really just touching things at individual points. And I actually really dislike the term testing as specification, because it's not. It's like touching something at a number of points. And this is a good example of the old Indian parable of where 5 blind men touch an elephant at one point and they can't see the rest of it. You end up with a very distorted view of the world. Like, one touches the side and thinks it's a wall. One touches the legs and they think it's a tree trunk. Someone else touches the trunk and they think it's a snake. These sorts of things. We need to get a much better surface area coverage and test much more for this. So when it comes to performance testing, it's really interesting. We need to test how systems behave as we increase throughput on those systems with different patterns of throughput. So you hear people talking about stress testing. That's not just performance testing. Stress testing is when I apply throughput to the point where it actually stresses and breaks. How does it behave at the point of stress? But I'm also interested in what is latency doing whilst I'm increasing what's going on. I also want to do it with multiple concurrency. I want to do things for long periods of time. Because another thing is people will test for too short a period of time to give a real view of what's going on. You don't see things like garbage collection, batch jobs, all of that sort of stuff that runs in the background. So testing's a kind of great area to look into. I'll talk a little bit in a second about some of the testing tools that are out there, but at the macro level, I've looked a lot into how people write code for testing, and I've also looked into a lot of testing tools. And quite often, this is how I feel when I look at the code. It is quite terrifying in many cases. Most of our testing frameworks out there, the J meters, the grinders, all of these tools, they quite often cannot generate enough load to really stress a system. We need to have much better testing tools that generate load on our systems, especially from single nodes. We end up just having to throw whole farms of servers to get some of the performance that we need. We should be building on the shoulders of giants and applying some good math and some good thinking. Because quite often I hear about people talk about things like averages. And averages, I think this is a really good example. So imagine you go for a beer with this guy. All of a sudden you go into a pub or a bar and you say, what is the average wealth of people now in this bar? All of a sudden, everybody's a billionaire on average. But that's misleading. It's unbelievably misleading. That's how a lot of people do performance testing, and they use averages. Averages are just not worth even looking at. We get multimodal distributions. We get huge variation. We need to have much better statistics applied. Capture everything, put them in histograms if we're going to measure stuff, or at least even look at medians and modes. Don't use averages. Little plea, please. Nobody use averages as we move forward. So a little quick shout out. Things like HDR histogram are really nice for measuring every single thing, and we can see a proper distribution for what's going on. And other great tools that are coming out now, like the Java Microbencmarking harness, is really nice for doing a lot of our micro-level testing. We need tools that go up to a higher level, and we have fun with using these. So actually, if you don't even have them, at least have fun writing them. So we've done testing. We know what the performance is of the system. We've been sensible. We're not talking about averages. We have got nice distributions. We've gone back and restudied statistics from school that we've probably forgotten about, and it's all really nice and useful. We want to dig in now and find out what the data is telling us. Well, in Formula One, they spend so much time analyzing the data, and it's really valuable. This is how they get really good. Michael Schumacher is Many people say one of the best drivers of all time, but really what he's even better at than his normal driving is his test driving. He would test drive 2 laps back to back, and the mechanics could change the vehicle, and he would drive it exactly the same, so you could take him out of the equation. He was such a good test case for the experiment that you took him out as noise in the experiment. And he would stay really late. He would stay till the last mechanic went home in case they needed more work, more driving, more work on the data. The level of passion and commitment, that's why some of these people are really successful. It's not just what you're seeing in racing on a Sunday. It's the hard work and dedication that goes behind and doing things like the testing. You also test a lot in real races. So like Adrian Newey, greatest car designer ever, and Christian Horner, who's now running the current Red Bull team, like they're just absolutely committed to getting the data and getting this all back into improving their process rather than being driven by the corporate normal ideas. And what they do to do this is telemetry has to be front and center. And that means we got to get much better at our efficient collection of data. Quite often, we do a lot of what we do without telemetry and without a lot of what we need in profiling. And frankly, it's witchcraft. That's the level of maturity that many people are applying to performance testing. We need to get better at this. So let's take an example of like a typical service that we're going to build. We'll ultimately store all of our data in some big bit bucket somewhere. And we're going to have lots of threads acting on that. But we're going to have many gateways taking data from customers. The thing that I find over and over again is queues are everywhere. They're absolutely everywhere. And we need to embrace them. And we apply things like Little's Law to find out what's going on. But if you're in the Java world, what we need to be able to do is monitor our queues. We need to know what size they are, how much data has gone through them at a point in time. All of our concurrent queues that we have in the JDK do not have the ability to read its size without impacting what's going on. They take a lockout on the queue to read its size, which stops you adding things to the queue and removing things to the queue at the same time. The size should be something that is an uncontended operation. They should also give things like flow rates. We should know how many things have gone through in the last period of time. And even making this sort of data available in production is so useful. So this is a kind of call out and a place. We need to get this stuff to be better. I spend a lot of my time developing data structures that allow real-time telemetry on them to work because the value that that gives in improving your systems and making them really, really fast. But we've got to be really careful, especially that we don't fool ourselves. Richard Feynman has cautioned us a lot about this, is that it's so easy to fool ourselves. We often are having to profile our applications. And one thing I've found a lot is profilers lie. They lie a lot. Many of our common profilers profile at a thing called safe points. And that is where the Java virtual machine has reached the point where it has stopped all of the threads to do something. Now, a thread that's stopped is not actually telling you what it's really doing. It needs to be at the point it's actually busy doing other pieces of work. We're starting to see profilers now that are addressing this and doing it better. So if we're in this space, watch out for that. Now, kind of moving on to the last section. I won't bore you too much with all the detail about profiling because that would just be cruel. Let's get back to this guy and why he's so fast and what worked really, really well. So how did he get to be so fast and so good with his level of understanding? He applied a lot of what we've just been looking at. He understood how things worked. He tested methodically. He got data on what's going on. This is a guy who's now in his 70s and is probably the best coach out there of modern drivers. He runs the Finesse Driving School, and some of the top Formula One drivers go to him. I've seen telemetry of him driving around a test track now in his 70s, making times that the modern drivers struggle with. And it's all because he's so super smooth. He doesn't need to be as fit as some of the modern drivers because he doesn't stress his body the same way because he's such a smooth driver. And that helps, and that gets it all working really very nicely. So you have to do some of this with finesse when you start applying it. So how do we consider putting this into action on a larger scale? I think fundamentally one of the things that's been learned from Formula One is the management and leadership side. And here's two absolutely superb examples. So Christian Horner, who now heads Red Bull Racing. Red Bull Racing was previously Ford Jaguar Racing. Previous to that, it was Stewart GP. Most people probably won't even remember Stewart GP or the Jaguar Racing side because they had very little success in how they actually went. Ford put loads of money in it and they run it like a corporation, and it didn't work. Red Bull took it over, put Christian Horner in charge, and he runs it like a race team. He staffs it with people who understand what's involved in racing. And so we need to staff our projects with people who know what's involved in software. I get terrified when I see CTOs and CIOs who don't write code. Christian Horner still drives on a racetrack in his spare time and loves it and is passionate about it. Michael Schumacher, Jean Todt is another great example. When Michael Schumacher joined Ferrari, they were nowhere. They were struggling to be successful. He agreed to come through on condition they brought through a really good team. So one of the other members of the team was Jean Todt. He also brought through 3 other members of the team. Many you may have heard of, like Ross Brawn and Rory Byrne, who's currently retired, but absolutely superb guys. In the first year, they struggled for success. Ferrari wanted to make an example of someone, so they wanted to fire this guy. Schumacher got all of the team, brought them in to the board and says, if we go, we all go. There's no making an example of one person because we're a team. They didn't fire them. That team went on to win 5 world championships in a row and stayed together. And this guy now heads Ferrari overall, the guy they tried to fire early on. The teamwork in getting this stuff right is so important. Now, everything we do, we're always going to be limited on resources, so we have to use those things wisely. The way I like to look at it is, let's have a transaction budget. So if I want performance, I want to set myself a transaction budget. So if I want something to happen in under 1 microsecond, I'll just decide how much I'm going to allocate the different bits. I'll use my telemetry, I'll use my profiling, then I can use my budget up over things. Then I can get great performance and I'm choosing where I'm spending stuff. I won't go waste my time putting in libraries and frameworks that start blowing my budget. I've got a simple rule on libraries and frameworks. They almost pay for themselves. You can put any library in you want, but does it pay for itself? Does it make things better for you in a measurable way? Otherwise, why are you doing it? We also have to react to load quite a lot. So in a car, we have things like suspension. How do we react to load in our modern systems? I find it comes down to 2 really important things that we need to build into our systems. We need to apply batching. This is a well-understood, great old discipline that seems to be lost on how we're doing modern things. And batching, when applied right, is incredibly efficient and very effective. You can do it in real-time systems. It's not old, slow batching. It's the application of batching to algorithms. And that lets you amortize the expensive costs. But then even more important to that is, how do I apply back off? So when things start to go wrong, I must back off my system rather than just let it fail, which seems to be a lot of the common ways. So how do you bind your queues? How do we have short circuit breakers, things like that, and that will make our systems much better responsive. And fundamentally, do we know how things work? A couple of really interesting ones is that I keep finding over and over again that most people don't realize all storage is tape. Disks are not random access. Sorry to burst the bubble for anybody who still thinks that, but there's a couple of orders of magnitude difference between if you deal with a disk in a sequential fashion versus dealing with it in a random fashion. That applies to some other interesting technologies, such as today networks are so much faster than storage. It used to be the other way around. Things have changed. You discover this from common measurement. The trip now between 2 machines in the same data center on modern 10 gig E, if you go to the extreme of kernel bypass, you're down at between 1 and 3 microseconds. Sub 10 microseconds is very, very common for what a network trip is these days. Most people are not aware. Going to an SSD is hundreds of microseconds. Going to disk is milliseconds. So if you actually want to have very reliable systems, replicate. Don't worry about storing to disk. Store to disk asynchronously. In fact, actually think about storage to disk is replicating to yourself in the future. It's an interesting way of looking at the world. It's also really important to think about how we access memory. This is something that's getting long forgotten. And back to the days when we used to build our machines, if you understand how the hardware works, you can get so much more performance out of it. And memory is just the same as tape. If you access it sequentially, it's incredibly fast. You access it in a random fashion, it's very slow. That matters with the data structures that we pick and how we start dealing with it. So it's all about the data structures and how we make that work. I'm going to kind of finish with one point, and that is that we're never done learning. We need to be active in our learning. I like to start virtually all projects with saying, to do what we need to do, what do we need to know? And be open about we don't know everything we need to deliver a project. So build it into the project plan from the very start. Just go out and find out everything you need to know, because that'll start de-risking it as much as possible. And understanding what's under the hood is as important as any of that. And on that point, I'll leave you. And you can all escape. And thank you very much for your time.
Thank you, sir. Thank you, thank you.
Thank you.
So, I guess this is it. I have some more beanies for those who are still here. And I can throw them out. And that's good, because it actually makes the flow through the wardrobe a bit less problematic. So this is the fun part, right?